Today we're going to be looking at infrared spectroscopy. The following are instrumental methods of structure and determination. One of them is the nuclear magnetic resonance, or NMR, the excitation of the nucleus of atoms through radio frequency radiation. Provides extensive information about molecular structure and atom connectivity. Infrared spectroscopy, or IR. It triggers molecular vibrations through irradiation with infrared light. Provides mostly information about the presence or absence of certain functional groups. Mass spectrometry, which is the bombardment of the sample with electrons and detection of resulting molecular fragments. It provides information about molecular mass and atom connectivity. And last, the ultraviolet spectroscopy, the UV, which is the promotion of electrons to higher energy levels through irradiation of the molecule with ultraviolet light. Provides mostly information about the presence of conjugated pi systems and the presence of double and triple bonds. Infrared spectroscopy deals with the interaction of infrared radiation with matter. The IR spectrum of a compound can provide important information about its chemical nature and molecular structure. Most commonly, the spectrum is obtained by measuring the absorption of IR radiation, although infrared emission and reflection are also used. Widely applied in the analysis of organic materials, also useful for polyatomic inorganic molecules and for organometallic compounds. The electromagnetic radiation is a radiant energy having dual properties of both waves and particles. Particles of electromagnetic radiation are called photons, and each has a discrete amount of energy called a quantum. Electromagnetic radiation can be characterized by its wavelength and frequency. Wavelength, by the letter lambda, is the distance from one point on a wave to the same point on an adjacent wave. Frequency is the number of waves passing per unit time. It is reported in cycles per second, seconds to the -1, which is also called hertz. Energy, or E, is directly proportional to frequency and inversely proportional to the wavelength. Here we show the effect of the electromagnetic radiation on molecules. You can see that as the energy increases, the wavelength, which is measured in centimeters, decreases. The energy in kilocalories per mole also increases. And here are the following effects. X-rays cause ionization. Near UV light causes electronic transitions. Also the visible light. Infrared radiation promotes molecular vibrations. Microwave promotes rotational motion, and radio frequency promotes nuclear spin transitions. The different forms of electromagnetic radiation make up the electromagnetic spectrum. Visible light occupies only a small region of the electromagnetic spectrum, from 400 nanometers to 750 nanometers. Here are some equations related to the electromagnetic relations. We have lambda as the wavelength. We have the frequency. We have c as the speed of light. We have E as the kinetic energy. And we have h as a Planck's constant. Here we show what lambda represents on the wave. The infrared radiation has a lambda from 2.5 to 17 micrometers and a frequency of 4,000 to 600 centimeters over 1. These frequencies match the frequencies of covalent bond stretching and bending vibrations. Infrared spectroscopy can be used to find out about covalent bonds in molecules. Here we show the delta of energy, which is equal to the Planck constant times the frequency. The frequency is represented with a V. We later have the Planck constant over 2 pi times the square root of the spring strength over the reduced mass. Spring strength represents the bond stiffness, while the reduced mass is, on average, the mass of the largest atom. As you can see, the frequency is directly proportional to the strength of the bonding between the two atoms, and it is inversely proportional to the reduced mass of the two atoms. Here we show the different types of criteria when we evaluate IR spectroscopy. So as the atom gets heavier, as you can see from hydrogen to deuterium to carbon, the frequencies or the bond energy decreases. This also means that the stretching frequencies, which is represented as centimeters over 1, decrease. there is a dependency on the bond energy as well. So single bonds to double bonds to triple bonds increase the strength of the bond, which increases the bond energy and also increases the stretching frequency. We can summarize it as the frequency decreases with increasing atomic weight, and also frequency increases with increasing bond energy. Infrared radiation is largely thermal energy. It induces stronger molecular vibrations in covalent bonds, which can be viewed as springs holding together two masses or atoms. Specific bonds respond to or absorb specific frequencies. Here, we first provide the equilibrium bond length, which is the regular length that the bond will have. This bond can be stretched and can be compressed in an equilibrium of motion. The vibration modes. Covalent bonds can vibrate in several modes, including stretching, rocking, and scissoring. The most useful bands in an infrared spectrum correspond to stretching frequencies, and those will be the ones we'll focus on. IR radiation does not have enough energy to induce electronic transition, as seen with UV. If the frequency of the radiation matches the vibrational frequency of the molecule, then radiation will be absorbed, causing a change in the amplitude of molecular vibration. IR spectra are most commonly presented as percent light transmitted through a sample as a function of the wavelength or energy of the light. Samples that absorb all of the IR light would give a spectrum with a horizontal line near the bottom of the spectrum. When a chemical sample is exposed to the action of IR light, it can absorb some frequencies and transmit the rest. Some of the light can also be reflected back to the source, as we show in here. From all the frequencies it receives, the chemical sample can absorb or retain specific frequencies and allow the rest to pass through or transmit. The detector detects the transmitted frequencies and by doing so also reveals the values of the absorbed frequencies. The IR spectrum is basically a plot of transmitted or absorbed frequencies versus intensity of the transmission or absorption. Frequencies appear in the x-axis in units of inverse centimeters or wave numbers, and intensities are plotted on the y-axis in percentage units. The graph above shows a spectrum in absorption mode. The graph above shows a spectrum in transmission mode. This is the most commonly used representation and the one found in most chemistry and spectroscopy books. Therefore, we will use this representation. IR bands can be classified as strong, S, medium, M, or weak, W, depending on the relative intensities in the infrared spectrum. A strong band covers most of the y-axis. A medium band falls to about half of the y-axis, and a weak band falls to about 1/3 or less of the y-axis. Not all covalent bonds display bands in the IR spectrum. Only polar bonds do so. These are referred to as IR active. The intensity of the bands depends on the magnitude of the dipole moment associated with the bond in question. Strongly polar bonds such as carbonyl groups C double bond O produce strong bands. Medium polarity bonds and asymmetric bonds produce medium bands. Weakly polar bond and symmetric bonds produce weak or non-observable bands. Infrared band shape comes in various forms. Two of the most common are narrow and broad. Narrow bands are thin and pointed, like a dagger. Broad bands are wide and smoother. A typical example of a broad band is displayed by the OH bonds, such as those found in alcohol and carboxylic acid, as shown below. IR is most useful in providing information about the presence or absence of specific functional groups. IR can provide a molecular fingerprint that can be used when comparing samples. If two pure samples display the same IR spectrum, it can be argued that they are the same compound. IR does not provide detailed information or proof of molecular formula or structure. It provides information on molecular fragments, specifically functional groups. Therefore, it is very limited in scope and must be used in conjunction with other techniques to provide a more complete picture of the molecular structure. In the region from 1,500 to 400 centimeters to the -1, vibrational frequencies are affected by the entire molecule, as the broader ranges for group absorption in the figure below, fingerprint region. Absorption in this fingerprint region is characteristic of the molecule as a whole. This region finds widespread use for identification purposes by comparison with library spectra. Although the entire IR spectrum can be used